Hi guys, let's review one more time about solving linear recurrence relations, but this is applied to actual counting problems. So this is the whole reason why we were doing this in trying to find these methods to solving recurrence relations. Okay, so I'm going to give you two problems, a bit of different nature. As I said, the hardest part here is to find a recurrence relation, and for you to be able to do that, you have to try all these various scenarios. They're kind of, we have seen in the homeworks things with rabbits or goats. There's about formulas for adding numbers. I'll do one for that. And there's another one you'll see I will do here about counting how many various ways you can pay something with various pay methods. Let me do the examples. The first one is, well, first of all, I'm going to define something called tk, and that is just the formula k times k plus 1 divided by 2. And this is called the kth triangular number. Now, what is that? Why is it called the kth triangular number? Well, because it actually is the number of dots you have if you would build a triangle with, let's say, k base k here. So you would always go one less, right? Each time you go one less. So the number of dots in a triangle like that with base k is exactly given by that formula. It sounds almost this formula for base times height divided by 2. It's not exactly that. But this is the formula for a triangular number. And so, for instance, T1, what that would be, of course, that's 1, right? And if you plug it into formula, you see that's also what you get. But if you just look at the number of triangles, what is the number of dots in a triangle of size 2? Well, that is 3 dots. And if I plug in 2 in here, I get 2 times 3 divided by 2, that's 3, etc. So the formula is correct. Now, the formula is correct, but you could actually prove it. So it is recursion, right? How would you prove it? Well, you would say, okay, how do you make a triangle of size k? Well, you take a triangle of size k minus 1, and you add just a base of k more. So we see that the recurrence relation of tk is that tk is tk minus 1 plus k. So this is a good exercise on trying to find the value for this triangular number. But I'm going to not do that. I'll leave that as a homework. So I set everything up, right? So I said, this is a recurrence relation, and if you solve it, you get this. That's the solution. I'm just telling you this, but it's something you should check yourself. That this is true. But I want to do a little bit more complicated. This is rather easy. It's not that easy either, but I want to do one step harder, and that is what I'm going to do is I want to now put all these triangles together. In other words, I want to calculate the sum of the first n triangular numbers. So this would be the number of elements that you have if you keep adding more and more triangles. So for instance, right, so what would this, let's call this an. So a3 would be the number of elements if you have a triangle of size 1, a triangle of size 2, and a triangle of size 3. So you see that this number would be, well, we would add everything, right? So it's 3 plus 6 is 9, etc. Okay, but we want a formula for that. Okay, so the question is, find a recursion relation for this function, this sum, where we know that tk is given by this formula. So we're assuming that the formula for tk we know, and we have to find that. Now, it is again something, right? So how do you make the next one, a4? What would that be? Well, you just add a triangle of size 4. In other words, you add t4. So we see that the recurrence relation is very simple here. It is to get the sum of the first n triangles. You take the sum of the first n minus 1 triangles, and you add the nth triangle to it, plus tn. And tn, we know that it is n over n. That is an minus 1 plus n times n plus 1 divided by 2. That's the recurrence relation. Okay, so once we have the recurrence relation, what is the degree? The degree is 1. So we have to need how many initial conditions? One initial condition. A1, right? And we have already calculated A1, I think, because what is A1? Well, that is just T1, right? It's just a single dot, so A1 is 1. We know that. Okay, so now solving. So step 1, we have to go to the homogeneous one. But this is a very easy homogeneous one, right? So an is an minus 1. So this is r equals 1, and that's there. And we know, by the way, that the multiplicity is 1 and then of this root. Okay, so this means that the homogeneous solution looks like a general polynomial of degree 1 less than that, so that is alpha, times 1 to the power n, which is, of course, just alpha. So the homogeneous solution is actually a constant. But remember, this constant we cannot determine yet. Step 2. The inhomogeneous one, so we're going to look at, we need a particular solution. Let me write it up. So what we look at is what is f of n. And f of n is n times n plus 1 over 2. Now that is a polynomial. So, okay, so here is s, m, and d, right? S is what here? Because we don't see it, we know that this means S is 1. What's the multiplicity of that? Oh, be careful, it actually is a root, the multiplicity is 1. And what is the degree? We talk about the degree of this guy, that is degree 2. Okay? Well, okay. So, we know that the particular solution is, what do we do? We take n to this power times a general polynomial of this degree, a plus bn plus cn squared times s to the power n, but that of course we don't write. So it is an plus bn squared plus cn cubed. Well, okay, it's a little bit of a... We see that because of we start already with a fraction, right? So it's there's gonna be some fractions there, but it's not too bad. What we need to do, we need to plug this into there, right? So get an plus bn squared plus cn cubed is equal to an minus 1. That would be an minus 1 plus bn minus 1 squared plus cn minus 1 cubed plus n over n plus 1 divided by 2. Well, perhaps now that I'm going to have to expand, well, let's expand everything. So we expand here an minus a plus b times n minus n squared minus 2n plus 1 plus c times n cube minus 3n squared plus 3n minus 1 plus, and now here I'm going to write this as n squared over 2 plus n over 2. Right? I need to see all the different degrees. Okay, so we compare this polynomial to this polynomial, meaning that the coefficients on the left-hand side must be the same as the coefficient on the right-hand side. The coefficient on the left-hand side for the constant, so for n to the power 0, there is none, so that is 0 on the left-hand side, and so this is the left-hand side, and this is the right-hand side, right? What do we have on the right-hand side? We have a minus a plus b minus c, and that's it, okay. What about the linear term? So the term n, we have a on the left-hand side, and on the right-hand side I have, these are, let me underline the ones with an n, not forget this one. So there's an a minus 2b plus 3c plus a half. It's the coefficient, right? Don't write n over 2, it's a coefficient that we want. The coefficient of n squared, that is a b on the left-hand side. Here we have this coefficient, and this one. So we have b minus 3c plus a half again. Okay, and then finally n cubed term. That's a c on the left-hand side. On the right-hand side, there's also only one that is c, and of course that's a void equation. So we have exactly what we wanted, 3 equations with 3 unknowns. Oh, but we can solve a little bit, right? Say these b's cancel here, and I see that 3c is equal to a half, so c is equal to 1/6. That's good, because now I can plug that into the next equation where the i's actually cancel, so I get 2b is equal to 3c, which is 3 times 1/6, plus a half. So there's a half plus a half, that is 1, so we see that b is a half. Good, now I can plug this all in here. We see that a, I'm bringing the a to the other side, is b minus c, and b was a half, and C was minus 1/6. So 3/6 minus 1/6 is 2/6, that's 1/3. So A is 1/3. So where we are at, the particular solution looks like 1/3 n plus a half n square plus 1/6 n cube. Okay? So last step, we have to put everything together. What is the actual solution? Will be a sum of one of these homogeneous solutions plus the particular solution. Now this homogeneous was just a constant, so that's what we have. And then to determine what the constant is, we name the initial condition. There's only one initial condition, namely n equals 0. N equals 1, sorry, I misspoke. That is 1 equals alpha plus 1/3 plus a half plus 1/6. But believe it or not, a half plus a third plus a sixth is 1. So this whole thing is 1, and therefore alpha is 0. So actually, the particular solution was the solution. But okay, that's in general not the case. So that's the solution. So in other words, this is the solution. This is the formula for the triangular, the sum of the first n triangles. Good, no? It's, you can regale your friends with something like that, and on the lonely and over. Yeah, nowadays we cannot party too much, so we have to do other kind of stuff to keep ourselves busy, right? Okay, so let's go to another problem. This is, let's say you have to pay postage. We have done this a couple of times. So pay postage. Okay, and so you have to pay n cents. Sorry, let me write it. Just n cents. So you start rumbling through your drawers and you say, "Oh my God, I have no big guys anymore. I only have 1 cent stamps." And then you say, "Oh, I have also 2 cent stamps. I actually have 2 times. I have a blue 2 cent stamp and I have a red 2 cent stamp." For the red ones, I don't know why I got the red ones, but I have red ones and I have blue ones and I have 1 cent stamps. Okay, so how many ways can you now pay n cents using these 3 types of stamps that you have? That's the question. Okay? All right, so let's start thinking about this. Well, so we have n cents, and we always represent it a little bit like this, right? So these are the n cents. And as always, what we look for is, I don't know what it is. Let's get it. So what we look for is, what's the last payment I make? Well, there are 2 possibilities, right? So let me get rid of this. There is either I paid with a 1 cent stamp, so a 1 cent here. And what is left then? Well, this is n minus 1, right? So this was n. So n minus 1 cents were left. Or the alternative was that I paid with a 2 cent stamp, but there are 2. Either a 2 cent blue or a 2 cent red. There are 2 possibilities that I have here. And what is left then? N minus 2. Okay, so now let's count all the possibilities. These are distinct possibilities, so we know that the number of ways that I can do this. The number of ways that the last payment is a 1 cent stamp is an minus 1. The number of stamps where the last payments where the last one was with a 2 cent. Yeah, so we keep the order is important, right? So it's like I'm putting them from left to right, and if I put it in a different order, then it's considered a different postage. Okay, so that's of course not true for the purposes of actually sending them the letter, but that's not the question. Okay, so what is for the second one? Well, there's now this what is left here. These guys I know I can do in n minus 2 times, and this one I can do in 2 different ways. Okay, this and they are independent, so it's the product rule again. So that is 2an minus 2, and these are disjoint ways of payment. So we know that this is just the sum, and so these are the recurrence relation. An is equal to an minus 1 plus 2 times an minus 2. It's a homogeneous one. That makes it a little bit easier. So let's solve it. Step 1. Okay, but what is the degree? The degree is 2. If the degree is 2, before we actually do step 1, perhaps let's find out on initial conditions. So, of course, paying 0, let's start from 1 cent. How many ways can I pay 1 cent? Well, only one way, right? How many ways can I pay 2 cents? Can you figure it out? 4 ways, right? Because I can do a 2 cent blue, I can do a 2 cent red, I can do 1 cent, 1 cent. Sorry, no, that's 3 possibilities. Because 1 cent, 1 cent, whichever order I do that, that's the same. So the answer is actually 3, not 4. So that's good too. You see, it's good to always actually work it out. These initial conditions, they are normally very simple to figure out. Although it could still be a little bit of work, but okay. So the 3 possibilities. So okay, step 1, the characteristic equation. Okay, these are powers of r. We start with degree 2, so r squared is equal to r plus 2. Okay, so that's r squared minus r minus 2 equals 0. Well, I put it this way. And so I'm going to factor this. So two numbers that factor to, that multiply to negative 2 and add up to negative 1, and it is plus 1 and negative 2, right? Yep. So I see that minus 1 has multiplicity 1 and 2 has also multiplicity 1, 2 roots. We need to know the multiplicities because that will determine our... Oh, I don't have to write a homogeneous, right? Because it is a homogeneous one. So, yeah, I should have... I said it, but let me write it down. Okay, so I know that this looks like minus 1 to the power n, and here 2 to the power n, and in front of that comes a polynomial of degree, general polynomial of degree 1 less than the multiplicity, so in both cases that means a constant. Okay, and then the last step is to find these, so we look now at the initial conditions. So you see the initial conditions is something you do always at the end, whether it's homogeneous or non-homogeneous, it's at the end of the problem. Okay, that's why they called initial conditions. Joke. Okay, so here is an. So we have a1 and a2, so we have to plug in n equals 1, then we get 1 equals minus alpha plus 2 beta, that's the result of plugging in 1. If I plug in 2, then there are 3 solutions, and on the right hand side I get alpha to minus 1 to the power 2, that is a plus 4 beta. Okay, so I can add this, for instance, 4 equals 2 beta, so I see that beta is 2. And if beta is 2 from this one, I can see that 1 is equal to minus alpha plus 4. So that means that alpha is equal to 3. So conclusion, the number of ways that I can do this is equal to 3 minus 1 to the power n plus 2 times 2 to the power n. You could write the last one as 2 times the power n plus 1, but it is better to leave it like that because it shows you exactly how it is written as a sum of these geometric sequences. And so, for instance, how many ways can I do, let's say, 8 cents? It's not much, right? I mean, there's no letter that is worth 8 cents, so, okay, how many possibilities I have? Well, that is, so A8, that is minus 1 to the power 8, that is plus, so 3, plus 2 times 2 to the power 8. 2 to the power 8, that is 4 to the power 4, that is 8 to the power 2, that is 64. So that is 3 plus 2 times 64, that is 128 plus 3, 131. I'm probably, again, made a mistake somewhere, but... Okay, so it's kind of quite a lot of many ways that you could do this, right? Okay, but that's when you keep order when order matters. And this kind of thing is always when order matters because we want to always look at what is the last thing you did and then compare to what happens before. Okay? I'm going to leave it like that. The problem will be something like that, perhaps a little bit more, the numbers, a little bit bigger numbers, but the principle will be the same. So you should be able to solve that problem. Either a homogeneous or a non-homogeneous one. Okay. So also again, if you want to test more, prepare more, prepare yourself better for this quiz, start looking at the homeworks, go do the homework solutions of this particular type of problem, try other things, similar things, okay? All right.